Second order systems. Previously we saw first order systems and we learned how to compute them, how to plot them, having the plot, how to write the transfer function from. We studied the definition of time constant and gain. Now we want to study second order systems. Second order systems can be written in the familiar form of the familiar equation 5. As you can see, we have omega n squared in the numerator, and in the denominator we have this equation. It has two poles, and it has two parameters here. One of them is omega n, and then one of them is either zeta or xi. So we are gonna study them. The pronunciation again is xi, 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 xi. So let's see. Go to equation mode. So this is zeta, and this is xi. Okay. So people use different ways to write or different symbols. A lot of people use xi, a lot of people use zeta for writing this symbol. Okay. Obviously, the standard form that we are studying here is not describing all second order systems. It's describing a family of second order systems. For example, equation 5 assumes no zeros. Obviously, you could have second order systems that have zeros. So what we are going to study today is for a specific family of second order systems that they don't have any zeros here. We also assume that the poles here, the poles of equation 5, both are on the left hand side of the imaginary axis. So we only study stable systems. We look at the roots of the characteristic equation, which are the poles of the system, and from them we find the behavior of the system, or we discuss the behavior of the system. Okay, so the first parameter to define is omega n. As we said, there are two parameters for a second order system, xi and omega n. Omega n is the undamped natural frequency. The unit of it is radians per second, and xi is damping ratio, which is unitless. It's just a ratio. If we combine them per equation 6, what is being resulted is omega d, or damped natural frequency. So what is undamped natural frequency? What is damped natural frequency? You have an equation and it has some damping. Undamped natural frequency is the frequency of oscillations of the system if you didn't have any damping. But you do have damping. So what you are going to actually see, the actual frequency of oscillations is not that. It's this, the damped natural frequency. So if you plot the behavior of the system or the response of the system, this is going to be what you're going to measure. So to find the poles of a second order system, we can try to solve this. How do you find a quadratic equation? Well, this very famous formula, we find out that we have two responses. We have negative 2c omega n plus minus square root of 4c squared omega n squared minus 4 omega n squared. If we factorize omega n squared and bring it out, or actually 4 omega n squared and bring it out of the square root, we can simplify what comes out with this 2 here in the denominator, and we end up having this. We end up having negative c omega n plus minus omega n square root of c squared minus 1. Now, notice that we don't know what c is. It's different for different systems. It's what we define here as damping ratio. If it's smaller than 1, we are going to have a negative value under the square root. If it's 1, we are going to have 0 here. If it's greater than 1, we are going to have a positive number here. So we are going to have, based on the value of C, we are going to have different scenarios. We have 4 different scenarios here. We have underdamped systems, which are the systems with C being, or damping ratio of them being between 0 and 1, which means that the roots are a complex conjugate pair, and we have an oscillatory response. We have overdamped systems. Overdamped systems are when C is 1. C is greater than 1. You're going to have 2 distinct real poles that are negative C omega n plus omega n square root of C squared minus 1, and the other one is negative C omega n negative omega n square root of C squared minus 1. Those are overdamped systems. Undamped systems is when you don't have any damping, so damping ratio is 0, which means that we have complex roots, only complex roots. And critically damped systems are when damping ratio is 1, which means that again we have 2 real roots, but they have the same exact value. Okay, so here, undamped systems. So undamped systems, when C is 0, you have 2 poles, both of them are imaginary or complex. You only have complex poles. For underdamped, C is between 0 and 1. You have 2 complex conjugate poles, so a pair of complex conjugate numbers. Critically damped is when C is 1, and you have 2 repeated, so you have the same number as your poles, and they are both real. And then overdamped is when C is greater than 1, and you have 2 distinct real poles. Okay, for system with transfer function g of s, what's the damping ratio? So the transfer function is given. Remember, for a second order system, we have this format. You should write your system first in this format. Is your system currently in this format? It's not. So what do? We divide the numerator and the denominator by 25 to write them in standard format. Now that it's in standard format, this is 2c omega n, and this is omega n squared. If this is omega n squared, square root of it gives me omega n. So omega n is 1 over 5. Then 2c omega n is 1 over 5 here. I substitute omega n with 1 over 5, tells me that c is half, which is between 0 and 1, and this means that the system is underdamped. For the closed loop system of equation 9, what's the natural frequency, or omega n, of the closed loop system? So again, you want to find omega n. What do? Well, we first simplify the system and write the transfer function. Remember, for a feedback system with g in the feed forward path and h in feedback, when the feedback is negative, the transfer function would be g divided by 1 plus gh. Here h is 1, so it's just going to be g divided by 1 plus g. And I can multiply the numerator and the denominator by s times s plus 2. And then omega n squared is 4 kp, which means omega n is square root of 4 kp. And therefore c is 1 divided by 2 square root of kp. Okay, now let's study the relationship between damping ratio, or C, and pole location. So I want to see, we studied this, right? We studied the value of C and what that means. Now we want to show that. We want to show graphically what happens. So it's basically a graphical representation of this table, right? So we want to show so plot these poles. Two imaginary poles are going to be the underdamped when C is 0. As I increase C, these two poles are going to move from the j omega axis to the left. When I increase C more and more, I end up here, and then I end up here. So it seems to me that these poles gradually go to the left. They meet each other on the j omega axis. After they meet each other, they apparently go away from each other. They take distance as I'm increasing C. So in this order. Possibly the most important case is underdamped. This is the behavior of a lot of physical systems around us. Just think about when your car falls into a dip or hits a bump. You have this oscillation or oscillatory behavior, right? We have an overshoot. So overshoot is the amount that you pass your final value or the desired value before coming back and then settling around it. So I wanted to start from 0 and go to 1, but the problem is that I actually pass 1 and go up to MP and then come down. So that MP is overshoot percentage or overshoot. What are other things here? We have TR or rise time. We have TS or settling time. We have TP or peak time. It's very clear, right? Peak time is the amount of time that takes for us to go to the peak, and then that obviously is equal to the amount of time it takes from the peak to come down again to the bottom part, to the minimum. How about settling time and rise time? Can we have a definition for them? Well, let's see. So peak time, the time required for the output to reach the peak value. Percentage overshoot is this equation. Settling time is the time required for the output to enter and stay within 2% or 4% or 5% depending on the definition of the final value. So the important part is to stay within. Why don't I say time required for the output to reach 2% or 5 or 4% of the final value? Why do I say to enter and stay within? Because if I say, well, time that requires for the output to enter or to get to the 2% of final value, so this is the final value, right? This value. When do I first reach to 2% or 5% of final value? Here. So the first time I get to 0.9 or 0.98 is here. I don't want that. That's misleading. I want this. This is settling time. So I have to wait until it actually settles down, and then it remains in the 2% or 5% of the final value, to the vicinity of it. Okay, for rise time, unfortunately, we have two different definitions. We have definition 1, which says the time required for the output to reach the input level. So for the first time, from 0, so the amount of time that it takes to go from 0 to here. And then the second definition says the time that takes to go from 10% to 90% of the final value.